Hello, and I'm doing yet another virtual contest today. Doing a Codeforces round 499, which is Division 1. And today I'm listening to Paladin music's I think it's like 30 most popular piano pieces or something like that. Because that's what I want to listen to. So starting in 10 seconds, we'll get to start right away. And 5, 4, normal countdown, 3, 2, 1. Alright, time to begin. Hopefully I don't fail. Set everything up and... alright. Problem A. Natasha is going to fly on a rocket to Mars and return to Earth. Also, on the way to Mars, she will land on N-2 intermediate planets. And then go back to Earth. Alright, so it's like going in a cycle, basically. Flight from X to Y consists of 2 phases. This way, huh? Flight from X to Y. Take off again. Oh, okay. The mass of the rocket, together with the useful cargo, is M tons. One ton of fuel can lift AI tons of rocket. This is a long statement. The weight rocket is 9 tons, the weight of fuel is 3 tons, the takeoff coefficient is 8. Then 1.5 tons of fuel will be right. 1.5 times 8 is equal to 9 plus 3. I see. You can burn non-integral minimum mass of fuel to load in the rocket. Okay. That's a pretty long statement, but I hopefully understand it. Alright, that works. So let's start out. So basically, we have like a bunch of, let's think of them as in a circle. These are the different planets we have to land. So now imagine between 2 planets. Just say this is like 1 and 2 or whatever. You have a cost AI, A1 for taking off here, and a B2 for landing here. Now let's say you start with X tons of fuel. So then I guess so after the first takeoff, you have to use M plus X divided by A1, right? That's what they're doing here. Because this is like the total weight, including the fuel, and then this is like the coefficient. So then you do X minus equals M plus X over AI. And then we need the minimum amount of fuel that Natasha should take. Well, it's probably easier to, instead of thinking about it going forwards, think about it going backwards. So let's do the trip backwards, starting from like landing on B1 and going backwards and adding the exact amount of fuel we need. So let's say, like at the very end, we should start with 0 fuel, right? So we want M plus X over B1 to be X minus M plus X over B1 to be equal to 0. And then that will be the value of X right before landing. So what do we need? So instead we can think about it as x minus equals 0. Let's solve for x in terms of y. Well, let's call this like x prime, and then solve for x in terms of x prime. So it'd be we have x times 1 minus 1 over, let's call this coefficient c, which will either be like an a or b, is equal to x prime plus m over z, right, divided by 1 minus 1 over z. Okay, so then now, this gives us the amount of fuel we need right before any operation. So like before we land on 1, we need wait, otherwise Natasha can fly to Mars to randomize the minimum. Okay. So x prime will start as 0, and then we'll work backwards through the cycle. So we'll add x prime, which is 0, plus m over b1 minus 1 over 1 over b1, and then then we'd add whatever that is plus m over n, an divided by 1 over 1 divided by 1 minus 1 over an. Hopefully that makes sense. But I'm still, when is there not a solution? That's the only thing I'm missing. If let's say x is less than x prime, would that mean there's not a solution, I guess? Because it's supposed to gain fuel? I think that's probably right. For now. That's all I'm saying for now. If x is less than x prime, there's no solution. Let's try coding that. First off, let's see. We'll need a IOMANA key for making sure we print out the decimal correctly. And then do cout fixed, set precision 7. And let's also define LD long double, so we don't have to type that. Now let's do it. Maximum is equal to 1, 2, 10. Oh, I guess maybe another thing we could have done instead is just doing binary search, which probably would have been easier. But, oh well. Is this good? I think it's good. Let me make it all. Should be fine like this. And first we see an N, and then M, and then we need to see well, the AI and B, right? Now we have to work backwards. So we'll let this be the return value. Let's see, what's that? LDX equal to let's make it Z. I prefer. Now let's look at the formula of it. We need a Z plus. Well, that's I guess kind of confusing, but hopefully you see Z is X prime, and here we need to do hold on, wait. I'll do a way to make this easier. So instead of having A and B separate, let's have them be the same. Then we can just do 4. Alright, let's just do this instead. You'll see why. This will make it not have to like write out this formula twice. So now for each one, we do is equal to into x equal to I plus j, not j. So as you can see, so like when j is 0, that means we're looking at like the AI value, right? So then we need to go forward an index, because like that's where it's landing. When j is 1, then we should stay the same index, since that's where it's like it's starting off. Now we do y is equal to z plus 1 divided by a of jx divided by 1 minus 1 over a of j. Let's multiply the top and the bottom both by z. So if we do that, the bottom gets multiplied by z. This becomes z minus 1. The top becomes z times this. Hopefully that makes sense. Maybe it's always possible, except for when AI or BI is 1. Should be like a of jx times z plus m divided by jx minus, and we need to make it into like a, well, not this should be. So because z is a long double, then like the numerator will be cast into a long double, so the division will work as we want. And then we do if y is less than z. Something like this. Let's see if this works. I guess it should be without the underscore. I always forget if it's with the underscore. Oh yeah, I'm starting pretty late today. Hopefully I don't make this a habit. It's even later than yesterday. But like today, I was like pretty tired, so then I just like went to bed in the afternoon. Okay, yeah, we also need to check. Not a of j. Jx. So here I'm just writing. Let's make sure this last one works. Huh? Why is this not working? So like I was pretty tired today, so then I just like slept in the afternoon, which is why I'm up now. So I'll probably be up all night, so like, you know, rip my sleep schedule or whatever. Okay, it just didn't update. Looks good now. Let's try the last one. And if the last one's good, we'll submit. Alright. We probably don't even need this condition. I'm guessing this is the only condition we need, but I'm keeping it anyway just in case. And I'm too lazy to prove. 14 whole minutes, that's pretty bad. Let's see what... Alright. On to B. Interactive for problem B. Okay. Set up the stuff, and Natasha is going to fly to Mars. Finally, Natasha sat in the rocket. She flies, blah blah blah. Okay. Let X define the distance to Mars. And X is bounded between 1 and M as an integer. Every question, answer the question is -1 is less than 1. So, at first it looks like it's just like a binary search. However, the rocket is broken. Precisely, let the correct answer to the current question be T. If the rocket answers this question correctly, it will answer T. Otherwise, it will answer -T. In addition, the rocket has a sequence of length n. Each element is 0 or 1. Okay. What's the bound on n? N is less than or equal to 30. Natasha, she knows its length. And m is 10 to the 9th. Alright, so basically, we want to binary search for x, which is bounded between 1 and 10 to the 9th. However, the query can answer incorrectly, so we need to deal with that. So the binary search will take 30, since that's like log 10 to the 9th, and then dealing with the cycle will probably take another 30. So let's try to figure out how to find when the rocket is lying or not lying. I have an idea, I think. So basically, imagine this is the number line. It's like 0, 1, here's m over 2, m over 4, m over 4. Okay, so imagine you're on the number line. Let's first query, our first query will be 2. And now, we're gonna just query 30 times 2. Why? So then, let's say we know that, on the ith time, it is, the same as the 0th time. Then that means we know that those are either both true or both false. How, like, if we get 1 the first time, 1 the second time, that means they're both true and both false, or both false. However, if we get a -1 the next time, then we know that this one must be a different, either this is lying and these two are true, or this is true and these two are lying. Oh wait, why are we answering? I was gonna spend an extra query. We can just do that all on one, right? So now we know whether the ith response is lying or true. And we know that because it's 1, if it's not 0, we know for sure it has to be greater than 1. So then after that, we can just binary search like normal, where we look at the middle value, see if it's greater or less than, and we just like account accordingly. That should be easy enough. So we need to have endl flush the output because it's interactive. What do I need to do? Alright, let's see. Let's make a query function. So for a query function, we need ret. Let's see how. Wait, how's the interaction? Oh, all you do is see out a number. Does it stop as soon as you get 0? Let's look. If the program reads 0, then you must immediately terminate the program. I see. Alright, so then there. Let's do this. Not return 0. Exit 0. Return ret. So this is saying, is ret greater than 0? Well, is ret not equal to -1, rather. Oh yeah, and we also need the y. Ret. And then we need to do not equal to a of y. Why? Because this will like make it the opposite of what it is, basically. So let's see. Let's see m. What do we get to read? We get to read m, and now first let's do our n queries to figure out who's lying and who's not. We do a of I, we do query I. Wait, let's have a separate counter k. K plus. Ret is equal to. What are we gonna do for this? Let's keep it as an int. Actually, I prefer that. Ret is equal to times equals. We'll do a of k, and then just k. Then we return it. Alright, so we're multiplying it. We'll have a of k equals 1. Okay. If a of k ret times equals negative. Something like this. Okay. So k is like a global counter that says, what query number is this modulo n? So now we do a of I equal to query I is greater than 1. No, if it's, let's see. y is greater than x. Else if y is less than x, it should be 1. Query 1 is less than 0. Okay. I think this is right. Now we just do normal binary search. Well, one is R2 if query mid is greater than 0. Right, if it's greater than 0, if it's 1, in other words, that means x is greater than y. And then by the end of this, it should have guessed the correct value. Let's see. Let's just do this. Just making sure there's no compilation error. And now let's try submitting it. Hopefully I didn't do something dumb. Well, that was a pretty dumb problem. Okay, yeah. Both A and B were boring. I didn't like either of them. Let's try C now, I guess. Astronaut Natasha arrived on Mars, and she has to pay a tax or something. And banknotes. Value of the ith banknote is AI. Oh yeah, because this is like round 499, usually older rounds have like a bit more standard problems, I think. Though sometimes they surprise me. But this is the most recent Division 1 I haven't done any problems from, which is why I'm doing an old round. Otherwise, I'd recommend to do like as early of a round as possible that you haven't done. And banknotes, ith banknote is AI. Finite number of banknotes. Martians have K fingers on their K. Okay. Oh, okay. In addition, the Martians consider the digit D divine. Thus, if the last digit in Natasha's tax amount is D, the Martians will be happy. Determine for which values of D Natasha can be. Okay, this is super stupid, right? Alright, basically, what we're doing is this. We want to say we have we have different amounts, AI, and we can use them multiple times. So we want to choose coefficients bi such that b1 times a1 plus b2 times a2, where b is all integers of our choosing, etc. This mod k is congruent. This is congruent to d mod k, and we want to see which modulos we're able to create, right? So that, oh wait, k is up to 100,000. That's kind of big. So it's kind of like a knapsack problem, but under modulo. Well, what do we know? look at A1 modulo K. Well, look at the GCD of A1 and modulo K. Let's take that as a GI for each one. And now take the GCD of all of them. And we should be able to make every multiple of that, right? That's just like standard number theory. Because like think a modulo is in a cycle. So if you start out, if you're like have mod 4, and you have 2, because the GCD of 4 and 2 is 2, you can only make cycles of length 2 with that one, right? But if you combine them, then you can make different cycle lengths. Okay, let's implement that. That's very easy. Max n equals 1 and 2. Actually, we don't even need to store anything, right? Let's call this m. I prefer m instead of k for this instance. And then let's see. And then let's let z equal to m, and then we let z is equal to m. And then we do cout. We need to read the input. And then we send the input, and then do z is equal to GCD z comma x. Right, that's taking the GCD of all of them. Now we should be able to make every multiple of that. Cout. So how many multiples are there? Well, there's m over z, of course. 4 is equal to 0. So then int I plus equals z. Cout. I cout 0. For int I is equal to z, I is less m, I plus equals z. I think that is it. That is rather boring. But yeah, this is a known thing where like the cycles you can create with like a generator, which is like you could think of a generator as a starting value that you take multiples of under a modulo. In the modulo field, a generator makes can make a cycle of like the GCD of it and the modulo value. So then you just do that. So then you think of like after the first modulo value, then you have a cycle under a smaller modulo value. So now you do the GCD with that and the next value, etc. Hopefully that makes sense. Okay, and submit. Alright. This was my least favorite one so far. Okay, it looks like it works. I liked A-OK, though it was mostly just a math problem. But A, B, and C were all not too interesting so far. Let's try Mars rover though. I'm guessing though the harder problems will be more interesting. Like a D and F. Natasha travels around Mars in the Mars rover and then suddenly broke down. Scheme is an undirected tree with a root in vertex 1, which every leaf is an input. I see. Undirected tree. Others look. There are 4 types. Logical elements take values from their direct descendants, input, return. Alright. And the number of vertices. Where it's high. Element. And what is the input? So you have 1 and is 9 and 4. You have 2 is in. Okay, isn't this trivial? Huh? I don't get it. There isn't even anything you're doing, right? You're just DFSing the tree. Is that it? That seems very dumb. Oh, here it is. I was wondering, what? For each input, determine what the output will be if Natasha changes this input. Okay, so we have like an initial input. Right, here's like the initial input. But then you're saying you flip each bit. What's the output after you flip the bit? That's more interesting. Cause then like your base, like if you just recalculated the whole tree, it would take a O(n) time. But you're saying they want like O(n) or n log n for trying to flip every single bit in the input. So basically, we need to say, how does changing one value affect the results propagating upward? Well, this is a bit more tricky. So if Natasha changes the 2 value to 0, then the output will be 1. Changes the 3 to 0, output will be 0. Changes the 3 to 0. So, wait, let's see. If he changes the n of 2 to 0, then this will be 0 and 1, which is 0. Not will be 1. 1 and 1 will be 1. 1 XOR 0 will be 1. And 1 and 1 will be 0. 1. Okay, yeah. So you can see that this like flips. This flips everything going up, right? This flips this node and then this node. So the question is, so we know that we can calculate like the original output value in O(n), right? Just by DFSing the tree and then just doing the operators naively. However, we know that for the answer to change, if we flip a bit, every single one of its parents must be flipped. Why is this? Because imagine if one of its parents weren't flipped. Then you could just like cut out the tree under that. Like let's say you change something in the subtree of 10, but then the 7 stayed the same. Well, you could just cut out the subtree, and then the rest would work exactly the same, right? That's why you need to know if when a value is flipped, all the parents will be flipped. So the question becomes, when a value is flipped, are all of its parents flipped? Well, we can pre-calculate ahead of time which edges, if you flip the value, will cause a change, right? We can say, like, first we pre-calculate this 5 will be the AND 1 and 0, and then we say, what if 7 is flipped? Will the AND change? We say, what if the 3 is flipped? Will the AND change? We do that for every node. And for the nodes that there is a change, we mark that edge with a 1. Otherwise, we mark it as a 0, right? So now, for all edges with a 1, now we can start from the top and just DFS all edges with a 1. And then for each of the end nodes we reach, if they were able to reach down all the way to that node from the top with only 1 edges, that means changing it will change the return value. Okay, and that's a solution. Alright, that was still pretty simple. What about, I don't know, that's still kind of boring. Why? That does not look fun. Let me read this one first before trying to code D. Binary tree with n vertices. Autumn's coming soon, blah blah blah. If a vertex fall off a tree, after that, fruits will grow on the tree. Exactly X fruits grow in the root. Arabesque. After that, the fruits grow on the tree. Yeah, the vertex. Number of fruits in each remaining vertex will not be less than the sum of the fruits in the remaining sums of the vertices. I see. Alright, so you're basically counting. So you have a binary tree, and you're basically allowed, you need a count for every, so you choose to cut out some subtrees, right? So you need and then for each of those ways to cut out subtrees, you need to count the number of ways such that the sum of fruits at each vertex is the number of fruits at each vertex is greater than or equal to the sum of the fruits at each of the sum of its children. Well, instead, let's think of them as like two separate problems. The first one.
Sorry, I'm not sure.
That was my Alexa. Alright, let's see. We know that. So instead of thinking of the condition as a... First off, let me write out the condition. So let's say we have a binary tree like this. 1, 2, 3, 4, 5, 6, 7. So let's say we have a binary tree like this, right? Let's say we start with the children having fruit numbers like this. This means node 2 must have more fruits than 1 plus 2, which is 3 fruits, because its children have these many fruits, and it needs at least as many fruits as its children. So we can say have 3 or 4 or anything higher, right? Now we say, same, let's put at 4. This one, we know, needs to be more than 7, so let's put it at like 10. We know this one needs to be more than 14, so let's put it at, let's say it's exactly 14. However, we're given the condition that we're given the number on the top vertex. So then we have to choose the other vertices accordingly, such that it's possible, such that the top vertex can be equal to the given value. So instead of thinking of the condition like that, think of it like this. Instead, so each vertex will be equal to, rather than setting it equal to the sum, a sum greater than the sum of its children, we're going to set it to any value greater than or equal to 0. Now, we'll say setting it equal to 0 will mean this vertex will equal the sum of its children plus the value written on that node. Right, so for here, if we wanted to make it equal, before we had it equal to what, 4? So then we instead mark it as 1. So it's like 1 plus 2 plus 1. Hopefully that makes sense. So why are we doing this? Well, this makes it easier to count, right? Because rather than having nodes that depend on their children, we can just say every node is any number greater than or equal to 0. The only condition that matters then is that the sum of the numbers in all the children... Wait, hold on. But what about when we are up here? We will need that the node up here will have to equal to, say it's a number greater than 0. What will be its real number? It will be equal to, so each node will be counted however many times it goes up to its distance. So like this 1 will be added to this node, and this node, and this node. So what we need is the number of ways to place values on nodes such that, let's say d1 is equal to distance to 1, and let's mark it as 1. No, let's mark it as 0. And then, this is just like normal distance, which is like the distance from the root. We say after marking all the nodes with any value greater than 0, we need the root to be equal to the value at the root. Let's call these A, so this is like AI. A1 plus A1 plus the sum of, am I doing this right? I'm doing this right. The 2 will be counted once, the 3 will be counted once, the 2 will be counted, will be added to here, the 2 will be added to there, and then its subtree has to be greater than this plus this, and so then this being counted twice, plus the sum of di times ai for all I from 2 to n. Is that right? This must be equal to m, or what's it given in the input? X. Oh yeah, I think it's counting the number of ways to distribute fruits like this, if we think about it in the way I described. And then when you cut off a tree, then you're like cutting off some of these terms. You have to say how many solutions are there when you don't have these terms. Okay, and how do you deal with? All right. Well, that's those are my ideas for now. I think I had some amount of progress. How are we going to deal with the solutions of cutting off them? It's probably going to be something like dp of what distances do we have? I'm not sure. Oh well, I'm going to go back to coding D because it is easier. Alright, so back to coding D. Yeah, I'm not sleeping either. Oh no. I'm a little tired. But I'm a little tired. But I need to practice, because I didn't practice, like, yesterday, because I was sleeping right after. Oh. Let's see, let's read in the input. So we need to read for all of the vertices. We read, first off we read. If, so let's just write out all the cases. If s equal to and, if s is equal to and, we set 0, 0, 1. Let's do a of I is equal to now we say if AI is less than 3, Cn I0 I1, else so like if the operation is and or XOR, there are 2 inputs. So we see in G of I0 and G of I1, else we just see in G of I0. Now let's think about we want like F. F will represent the current bit value. How long is that? I don't know. This doesn't seem like the most interesting round, I guess. Well, practice, practice. It's DFS, I. DFS. Let's do it like this instead. And then let's one index them. No. Let's... Right. Let's set let's say I 1 is equal to negative 1. 0 is equal to 1. Something like this. So negative 1 means there's no children. Now we'll DFS. It's C, 4, 0, 2 is negative plus. If V of CI, DFS, V of CI. Now we do. F of PSC 0 into X of PSC 0 C1 F of X and F of Y plus 5 and F of I 4 XOR y plus if 3 y is equal to not x. Alright, this should be all the cases, right? Must be hungry. Oh well. Alright, this should be all the cases. Now we also need to do what do we need to do? We need to do 4 0. Now we need to try flipping one of the children bits, right? Let's say, alright, wait, let's make a function, say f of I to ff of c. Oh wait, this should all be c anyway. So ff is going to be a function that is pulling up these values, I guess. First off, all these C's should be C, just So I just return FC. Alright, this is going through all the cases. Now we say f of I is equal to f of c is equal to x. Now we say grci equal to f of c is not equal to f of c not I. I Alright, basically we're saying, wait, no, let's, look, what is my, okay, we actually are gonna one index them. This part nicer. So if we one index them, that allows us to do this. This is equal to x or equals f of. So now, if it's 0 index, we'll just XOR by a 0, right? And then alright, this should be good. So like, imagine one of the children doesn't exist. Well, it doesn't even matter, right? Because if one of the children doesn't exist, then we'll just XOR by f of 0, which will just always be 0. And then that value won't even be used anyway, right? So like, if GFC1 doesn't exist, then y won't be used anyway. Yeah, okay. Now we say f of c is not equal to f. So now we're saying, if these, when we flip this children, is it different? If so, let's just do this. So now here's where like we're setting the edge as existing. Okay, now we need to do one more DFS. So our second DFS now here is where we're DFSing down only the marked edges. Then we say if a of I, a of c is equal to 4. Why do we put this? C. If a of c equals 4, we mark all the nodes that we reach as b of c. Now we can just go for 1, if a of I is equal to 4, we see out f of 1 XOR b of I, because b of I is like a can the value change when this bit changes. Hopefully I did that all right. Oops, there should be an int. I wonder how short my code is compared to others. I think I did this pretty efficient. Oop. But not correctly, I guess. What did I do wrong? What did I do wrong? Why does my stomach keep growling? That is annoying. This one. C, because one index. Alright, let's see what we're getting wrong. Alright, 9 is 1. 6 is 0. 3 is 1. 8 is 1. 2 is 1. 10 is 1. 7 is 1. Why is 7 1? Oops. That would explain it. Okay. Now 7 is 0. 5 is 0. 4 is 0. 1 is 0. Oh wait, this should be DFS2, idiot. Alright, let's see. Okay, now we're getting it right. I don't need this. This should be right now. Oops. Alright, that wasn't too bad to do, I guess. Yeah, I don't know. It was a okay problem, but definitely not a, like, nowadays div1d. Now it would be like a div1b, except then people would complain it's long implementation, because it's a whole 57 lines. Okay, my implementation is pretty short, which I figured. Okay. How am I doing? Obviously, if it was a real round, I would have coded this right away, instead of thinking about F first, but in practice, I am more lazy. Natasha was already going to fly back to Earth, when she remembered she needs to go to the Martian store to buy Martian souvenirs for her friends. It is known that the Martian year lasts X max months. Month lasts Y max years. 2 months in a year were selected, 2 days in a month, 2 seconds in a day. Then the store works these moments, okay. I see. Oh, okay. This statement actually ended up being kind of interesting. Alright, so I think it has all this talk about days and months, but it's better to think of this instead as 3D coordinates. So imagine a 3D plane. You're basically saying you have 2 points. It might be better to draw it like this. Basically saying you have 2 points, and then all the points inside of here represent days that the store is working, right? So you can think of this as like the months, then the days, and the seconds or whatever. So like whenever the months are in the range, the days are in the range, and the seconds are in the range, then you know that it's a valid day. Otherwise, it's not a valid day. And however, you don't know what the bounds of this cube are. But Martian tells Natasha n points that are inside the cube and m points outside the cube. So what you need is 2 different things. You need what is the smallest cube bounded by the endpoints? If a query point is inside of that, you know for sure it's like a good point. Next is, what is the largest cube? Bounded by the m points. If a point is outside that cube, then you know it's definitely closed. And for any points in the middle, you're not sure. So let's think about the first problem. How do we think about the smallest cube that can fit all points inside of it? Smallest cube that all points can fit inside of it. Oh, and of course, Martian is mistaken, incorrect, if like the smallest cube bounding the endpoints has one of the m points inside of it. Is it just that for the cube we see what's the greatest y in the n, what's the least y in the n, etc.? Oh yeah, also it's not really a cube, it's a rectangular prism. And then once we have that, we can see what side of the cube each of the m points is on. And based on what side it's on, we can bound it. Okay, I actually think that's pretty simple. Never mind, it didn't end up being very interesting. Now this is a really easy contest. I don't think I want to code that yet. Alright, I'll code it at the 30-minute mark. Well, I'm more interested in F, because it's the only problem that has not taken me more than like 5 minutes to solve in my mind. Solve. F tree. What is the solution for in the tree? So we thought a decent amount about like when we have a static tree, how many ways are there to put the fruits. Now we need to think about, given how we're going to deal with like cutting off subtrays. Well, imagine at each node we had a... Alright, let's see. I have to fix this again. No. Uh-oh, that's not good. I did something dumb. Stupid stylus. Come on. Don't get stuck. Shoot. That's not good. Let's see, can we get my stylus? And... come on. Why does my stylus have so many problems? Okay. Basically, my laptop has like a stylus holder thing in it, but it's broken, where the stylus can't go all the way inside. But if you don't put the stylus inside every so often, then like it's disconnected from the computer for some reason, and you can't use it. So then, that's kind of a pain. Well, worse things could happen in life. Anyway, back onto the tree. What do we need to think about? We need to think about... oh yeah, we were saying, let's say a node had like a DP of current node X. This represented the number of combinations such that what? The sum of fruits is less than or equal to X. You could transition from a DP of I, like a knapsack way. It's like DP of I. Y. We know Y has to be less than or equal to... what? It has to be less than 2 times X. Because Y will be added here, and it'll also be added here. Well, that's kind of interesting. Y has to be Y is less than or equal to X over 2. Or let's just call this X. No, let's call this Y. This will go to like dp of X plus. So you have the sum of the subtree in here is Y, and the sum of the current node plus equals Y2. So it's 2 times Y. And you basically start out with dp of a C X for every X equal to 1. No, equal to X. Because you're saying the number of ways to have a sum that's less than or equal to X. It doesn't have to be exactly X. Wait, is that what we want? Is that what we want? Less than or equal to X, or less than X? It's less than, well, yeah, let's say less than or equal to X. And then what we do is say dp of cx plus equals dp of cx plus equals what? Then for each child, we'd say dp of cx plus 2 times y times equals this or whatever. Oh, another thing is we know the tree's a binary tree. Right, it gives us that. Alright, we know the tree is a binary tree. That just makes transitions easier if we were to do this. As we know. Let's let this node be C, this be I, this be J. Then dp of Cx be equal to the sum of y plus z let's say dp of right, let's see. Sum of y plus z is less than x. We're saying a dp of cx is the number of combinations that make a tree with exactly this sum. Less than or equal to x. Two times dp of I y times dp of j z I y times jz. Right, that's basically it. Because that'd be like, this is the sum of these subtrees. We know that the current node has to be greater than, has to then be equal to y plus z plus some amount. Did I read this correct? Oh wait, is it only the sum? It has to be greater than the sum and the direct children, I guess? Number of fruits. Be less than the sum of number of fruits, the remaining sons. Less than the number of fruits. So that is the sons the direct children, I guess. Okay, so we're gonna say instead just that. Instead, dp of cx equals the number of ways to put fruits in the subtree of C, such that the node value of C is equal to x. Now of course this dp won't work, right? Because in the statement, x is up to 10 to the 18th. So we need a better way to count this. But you can think of it binary tree. I'm guessing this is going to be like a polynomial multiplication problem. We basically have 3 operations, right? Have like a a convolution. We have when there's two children. Otherwise, if there's one children, we just say dp of cx equal to sum of a dp of iy, where y is less than x. So we just need a... So it's like doing the prefix sum over the polynomial, dp of iy, right? And then if we did that, and we're starting out with all the leaves, just have the polynomial x. Right, yeah. Oh wait, no matter what, we have to also do like the prefix sum. How do you do like a prefix sum of a polynomial? Like x squared plus 3x plus 5. You want to convert this to when it will be like 4x squared plus, no, 3 plus 5 is 8 plus 9x squared plus 8x plus 5. You need to be able to convert polynomials like this. Okay, I'm starting to get tired. Well, I'm not sure how to do some operation. Well, okay, the polynomial in terms of each node will only be up to the size of its subtree. It's a binary tree. I'm not sure. I don't know. I'm pretty sure it'll be something with Lagrange interpolation, doing this dumb polynomial stuff, but I can't figure out an exact idea. So I guess I'll code this one, since I now have 30 minutes left. And probably Timmy Feng and Geothermal. I've got this. I guess not. Alright, let's see. Well, this one, the D was pretty easy to figure out, but at least it was kind of fun to code. Let's see, now we have accents, 1, 2, 3. Wait, no, wrong problem. We're coding what, this, right? We don't actually care about these values, I don't think. They're just here to show bounds, but oh well. NMK. I don't actually care about these at all, so I'm just going to do it like this. Well, these are queries, so we're gonna make this Q instead. Now we're gonna say int a3 So we should be able to solve each dimension completely independently. Alright, so go through. Well, let's make the number of dimensions k. Then let's set So A will be the lower bound, B will be the upper bound, right? No, wait, that means we should make A equal to this. So we'll say A of J equal to min x sin x. A of J is the min A of J times x. A of J is equal to max of B of J x. Now let's go for Y. Actually, let's do it like this. Now let's go to the M. Now we need to get the bounding box on for the outer. So let's num set B of 0. Alright, num copy B, A, B, Now we say if x is greater than or equal to A of J 0 and wait. So we need to see if all three dimensions are inside. That means it's inside the box and it's invalid. Let t equal to 0. X is less than A of J 0. B of J 0. And then B of J 0 x. And how we do. We do what? If x is greater than A of J 1 for x. Alright, so here, this is like the inner bound box that has to be bounding the n points. And then now we need the largest box that the m points surrounds, that the box surrounds the inner box. And then if not t, see out. Incorrect. No. Let's see out. minus key of 0. Alright, now we're saying the bounding box has to be. We're saying the points outside of here are good. Wait. I gotta do this right. No, I should be doing not like this. I'm supposed to be creating. What am I supposed to be creating? The box where the points are inconclusive, right? Alright, so instead, we should be doing this. So, B. B of 1. Now we should be saying this is equal to max. And then if all of them are inside the bounds, then now we do. Now we answer the queries. Q minus minus Q. C. Alright, let's just do int. We do X, AZ. We do ZA and equals. X is going to be equal to, we have 0. Y is going to be equal to 1. Now we see out CA sure. Open CB sure. This should be post, colon, did we do this alright? Let's find out. So we're seeing if it's outside of this box, if one of the coordinates are outside this box, then it's closed. If all of the coordinates are inside this box, it's open. Otherwise, we can't be sure. A of J, where did I do that? J0. Why is this J1? Correct. Open, closed. Oh, this one's saying closed. Why is it saying that? Let's print out the things we got. v-bounds. Huh? Where's this getting 0? This shouldn't be 0. Min? Oh, wait, oops. Alright, let's do this. 4, 2, 0 to be 1. I should have made the 2 index first, so we can use memset. Oh. Okay, this looks like it's probably correct. Let's just comment this out, because we might have to print it. It's not working, but I think this will work. And it was pretty easy. I'm not sure why my friends list people have not solved it. Oh well. Alright, and will we get it? Hello? Do we get test 3? Nope. Alright. What did we do wrong? Let's print this back out. I'm not too sure what I did wrong. So here we're bounding smallest box that fits inside points. Now we need to bound, think like if the point, like imagine for this side right here, you had a point to the left of this. That means for the M box, you'd have to make its side on that side be up to there. So what am I doing? Anything outside of there, you know, is good. What do you? Yes. Wait, hold on. Okay, I thought about the M points incorrectly. So think about each of the M points as either read again. For each of the M points, we have to think about what do I have to think about? Oh yeah, for each of the endpoints, let's say it's like greater than all 3 of the dimensions in some way. That means we only know that if a point is greater than in all three of these dimensions, we'd know it's true, right? It's closed for sure. But otherwise, we don't know which of these dimensions it was not good in. If it's only greater in one dimension, it's like a line outward. Well, we know anything with that dimension. It's fine. Well, basically, we only have like not very many cases, and we can do them all separately, I think. Wait, no. I see. So dealing with the closed case is going to be a lot harder. Lebensraum by who's it by? I don't know. Lebensraum by some Litz. It's by Litz. I don't know how to say it. Alright. So I guess this problem is more challenging than I first thought. Not too sure how to deal with this. So we know any point outside of here will be for sure closed. What if it's only greater than one of these dimensions, or even two of them? We don't know for sure. And the problem is that this will create like a jagged shape. So points only on here will make a plane. If you're to the right of the plane, it's good. Points that are greater than 2 dimensions will make like have 2 planes colliding. Or if you're outside the 2 planes, you're good. So first off, just think about the full planes. That will create a box, right? What about the 2 planes? Then you have to deal with those sort of separately. Or like both of them have to be inside the current plane bound box, because otherwise it's useless information. Is it? No, it might not be. Wait. Yeah, it is. Yeah, it is. Basically, you have to think about the corner of the box where outside the box is a closed point. You'll have like 2 planes that are right, and then you'll have some sort of inside squares that you're out if you're outside of this. Those are also good. They may be multiple and they don't exactly line up. And then you can also have like the 3 planes colliding, where if you're greater up here. So how do you deal with all of those at the same time? That's definitely pretty challenging. Right, yeah, this problem is actually more interesting than I definitely first thought. And I only have 8 minutes. After this, what I need to do, I need to study for Spanish, do other that in environmental science. How do we test if a point is outside the shape? Because it's not too... Okay, we must have to do the queries offline, right? There's no way we can online test this. So let's say the queries are offline. We're gonna sort all the queries by X. Let's say for a fixed X. For a fixed X, then we'll have like different planes that are currently in scope. That, if we're in that, then we are good. So then we need to test which of the points are good planes. It's only a single point, right? Yeah, so you can sweep across and then query. Is a point bounded by any rectangle? Well, that's still too hard too, right? Is there any data structure that, given a set of rectangles, we ask, again, is one of our current points, can we test query points to see if a point is inside any of the rectangles in the data structure? And the points, and they're up to 10 to the 5th. I do remember a problem that was like a... I'm not sure. Yeah, I don't know. I'm not having any ideas right away. Yeah, I think I'm pretty stuck. And I'm kind of tired. 5 more minutes. I guess I'll wait the 5 minutes so I can see what the editorial says. But yeah, I've basically given up. Let's look at how long our code is, I guess, compared to the friends list. Of course, Timmy Feng. Okay. And yep, that's about expected. My code is usually the shortest on harder problems, but Timmy Fang and Game Game are shorter on shorter problems. 4 more minutes. Sure you can't. I think it will be offline queries, where you do a sweep in the X direction, and then use a data structure on the Y and Z direction. Oh, let me think. There's this problem I did. What was it from? Must have been from COCI. Was it this? No. What is it? This? I remember this problem about counting like the number of intersecting rectangles. It's not that similar, but maybe some idea from it is used. Here how to count intersections of rectangles in one 2D plane. Instead of counting number of... Oh, okay, yeah. This is the problem. You have rectangles in like a 2D plane. Well, you have rectangles in 3 dimensions. Is it in 3 dimensions? Yeah. You have rectangles in 3 dimensions, and you're counting the number of intersections. Well, you can say this is very close to the same, I think. Or, is it rectangle? Let me look up this problem. Right, it's rectangles, and it's finding the number of pairs of intersections between 3 rectangles. I don't know. I think you can probably use a similar idea to this, but I don't really remember what you did in this problem. I just remember taking a while on it. But I'm guessing it's something like can count. You could use that somewhat similarly. Say, count the intersections between rectangles originally, then add the points as like infinitely small rectangles, and then count the new number of intersections or something like that. However, that has, you're not given exactly rectangles, but different like bounds. I don't know. With like whatever way you solved this problem though, with a binary index tree. Maybe you could do that the same in a sweep. Maybe you could do that the same way. I'm not sure. But alright. We did pretty good though. We got 1/13th. And even though like we took forever on this because we first thought about f instead. Let's see. Let's quickly look at the editorial and see if any of my ideas were anywhere close for E and F. M equals 0. Two-dimensional segment tree. Oh wait, they're just using a 2D segment tree and setting a range equal to 1. Duh, that's easier. And then query the point. Because I was thinking... Okay, yeah. I think they're doing exactly my idea where you have to do them offline. Sweep through the x-axis. Then you just hold a 2D rectangle of you use like a lazy operation on the segment tree to mark rectangles as existing or not existing. And you just query the point to see, is there any rectangle over that point? I guess that's not too bad. I don't know why I wasn't doing that. And then F. So indeed, it's like some generating function. Well, this looks complicated. Nice meme. Well, that looks like a bit much for me. Maybe I'll read about it later. But it looks pretty hard. This one, I think I could have got this one. I was like pretty close. All I needed to do was lazy set on a 2D segment tree. I was thinking like 2D segment tree, but I was thinking, no, that won't work. Because I forgot like lazy operations exist, I guess. Oh well. But that went pretty well compared to our other virtuals, I guess. Mostly because the ABC were so boring, and then D was pretty easy still. Let me see how Timmy Fang coded it. Yeah, somewhat similar, I guess. Okay, well, oh well, that's all for today, I guess. Wasn't my favorite div one, but D was fine. E is interesting, and F looks impossible but interesting. But that's it. Adios, I guess.